previous video, we have discussed the electric field intensity due to dipole on the equatorial line, right? So in this video, what we will see the electric field intensity due to dipole at some general point. So this is what we will see. Because in this case, we will not take any point on the center of the dipole, neither on the axial line, neither on the equatorial line. That will be at a random position, right? So we will start with our first step, that we will consider a dipole AB. First, we will consider a dipole AB, right? So this is the AB dipole, all right? So we know this charge is minus Q, this is plus Q, right? So this is how a dipole is constructed. Now, if you see, this is the center of the dipole. The separation of the dipole also we know. That means the length is what? 12. Clear? Now, what we will do, we will consider any point P. This is a point P, which is at a distance R from the center of the dipole. Clear? So this is what we have written. AB is a dipole of length 2L, center at O. P is any point where the electric field has to be calculated. That means at this point P, we will place any test charge Q0. This is what we do when we calculate the electric field intensity. All right. Now you know that the direction of electric dipole is negative to positive. Okay. So from the direction of electric dipole, we will make an angle theta. We need to remember this angle theta is taken from the direction of the dipole moment. That means if you're taking any point in this particular direction and minus Q is this side, plus Q is this side, you cannot take the angle theta to be here because the direction of the dipole is this. So you will have to take from this direction. You will have to write minus Q this side, plus Q this side. And this side will be your dipole direction. Then you can consider this to be theta. Clear? So I'm writing it here that theta is the angle taken from the direction of dipole. Clear? Now we can see here R and theta. These are two coordinates, right? And we know these coordinates are the polar coordinates. Okay. So what we will do is we will use the polar coordinates to find the electric field intensity at some general point. Okay. Due to a dipole. So now if you see, this is P. Now we will do the vector resolution. When we will resolve the vector, means when we will resolve this P, the dipole, we can write this to be as P cos theta, right? And the projection is taken to be on this side, which is the P sin theta. Clear? So here what you will see is P cos theta and P sin theta are the components. These are what? These are the components of the dipole moment P. Okay, the dipole moment P. All right. Now, if you see here, this P cos theta can have electric field in the axial line, right? Along this, like parallel to it, we can have an electric field which will be E parallel. So P cos theta will be the component for the parallel electric field. Similarly, if we draw a perpendicular in this side, that is the perpendicular component of electric field. So you can see this is your P sin theta, this is your what? E perpendicular, that is on the opposite side, right? So this is your E perpendicular. That means P sin theta is the perpendicular. This is for the perpendicular one, and E parallel is for the P cos theta. Because if you see, you can get electric field parallel to it and you can get a electric field perpendicular to it. Axial line electric field is also called as E parallel, and equatorial line electric field is also called as E perpendicular. Okay. So you will have to note that E parallel. So you will have to write it as a note that P cos theta is your E parallel, right? This is your E parallel, and P sin theta will have the perpendicular electric field. Clear? Now what we know, the formula for E parallel was 2kp by r cube. This is what we are having. But this P will be what? This P will be P cos theta. All right. And what we know, P E perpendicular was kp by r cube. So here what you will have, P sin theta. That means E parallel has the dipole component P cos theta. E perpendicular has P sin theta. So this dipole is written for parallel P cos theta and perpendicular P sin theta. All right. Now if you see here, this is your E parallel and this is your E perpendicular. So the net electric field will be here. This is your E net, that is the resultant electric field. So we already know what is the resultant electric field. How we calculate using vector? It is the square of the first vector component, the square of the second vector component, right? Plus twice of what? The first vector component, the second vector component, and cos theta. Now, if you see here, this cos theta is cos 90 degree. Why? Because the angle between E perpendicular and E parallel component, it is 90 degree. You can see this angle is your 90 degree. So cos 90 is your 0. So this entire term will be what? 0. So you will have the net electric field, that is the resultant electric field is what? E parallel square plus E perpendicular square. All right. So now we will just put the values here. So the net electric field E, it is equals to root over. So what do we know? E parallel, it has value what? 2kp cos theta by r cube whole square plus E perpendicular is kp sin theta by r cube whole square. All right. So now on simplification, if you see this kp cos theta by r cube and this kp sin theta by r cube. Okay, here 2 it's not available in the second term. So we will take common kp by r cube, okay, with a whole square. And this root over, I'm writing it here. And what will be there inside? It is 2 cos theta, right? 2 cos theta. If you will do 2 square, it will give you what? 4. And this is your cos square theta. All right. Plus, you will have your sine square theta. All right. So now you can take this term outside because square and root over will get cancelled and you will have E is equals to kp by r cube. And within root over, you are having 4 cos square theta plus sine square theta. So how you can write 4 cos square theta? You can write it as cos square theta, 3 cos square theta plus cos square theta plus sine square theta. This is how you can write. So if you see here, cos square theta plus sine square theta is 1, right? So you can write electric field E is equals to kp by r cube, okay, root over 3 cos square theta plus 1. All right. So this is the electric field at some general point. Then this is what you're having. Now you see special case. That means you can check this particular equation taking theta is 0 degree for the axial line, right? So first of all, if you write, if theta is equals to 0 degree, that is for axial line. So you will get directly the formula. Okay. Theta is 0 degree, cos 0 is 0 what? 1. So this will be what? Kp by r cube and this will become your 1, right? So 3 plus 1 is what? 4. So root over 4 will give you what? 2, right? So this is electric field intensity. So you can see this was the same for the axial line. Similarly, if you take, if theta is equals to 90 degree, okay, that is equatorial line. For equatorial line, you'll get the answer. You can write, we know cos 90 is 0. So this entire term will become 0 and this is 1. So you will have directly E is equals to kp by r cube. So you can verify and check whether this is correct or not. And if you want to really remember the formulas to calculate numerical problems and all those things, so you always remember this general point equation. So, and just put theta 0 degree for axial line and theta 90 degree for equatorial line, and you can just get the formula directly. Okay, so here you have just calculated the magnitude, right? So now what we will see, this net electric field, right? This will have a direction also, right? So we will see how we can find the direction of the resultant electric field. So for this, we will draw the figure once again here. If you see here, this was your AB dipole, right? So this was your minus Q, this was your plus Q. This was the center, and here, this was the direction of the dipole. And if you see, this was the point P, which was at a distance R, right? So in this direction, we have taken E parallel, and perpendicular to it, we have taken E perpendicular, okay? And this was the net electric field, E net. So if we draw this net electric field at this position, okay, E net, if we draw here, and this was your angle theta, what you can see, this resultant electric field, it is at an inclination of how much? Theta plus phi. It is theta plus phi, okay? Not phi plus theta. Theta plus phi, because this is in this particular direction. So it is theta plus phi from the dipole, okay? And how you will calculate the direction? You can write tan phi. We know the formula for tan theta is what? Perpendicular upon base. So E perpendicular upon E base. It is parallel, okay? This is base, this is your perpendicular. So we have already calculated the value. So for E perpendicular, it was Kp cos theta, right? Or sin theta. It was sin theta. Perpendicular, it was sin theta. Kp sin theta by R cube, okay? Divided by E parallel component, it was what? It was 2 Kp cos theta by R cube. So if you see here, Kp and Kp gets cancelled, R cube and R cube gets cancelled, and you have tan phi is equals to 1 by 2 sin theta by cos theta. That is what? That is giving you tan phi is equals to half of tan theta. So this is how you can calculate the direction, and you can write here the net electric field, okay, is at an inclination of theta plus phi, okay, from the dipole moment P. So this is the entire derivation of the electric field intensity at some general point due to a dipole. So that's all in this video. Thank you so much. Have a good day.